Okay, so today we want to look more at this resistance thing. We've been looking at the tolerances and errors in resistances. Today we want to look at wire resistances. So let's say that we have a wire that is 200 feet long and it has a tested resistance of 0.4 ohms. If I get another wire, this new wire is 500 feet long. Should it have more or less resistance? It should have more. Okay, 1.0. Resistance and length are what we call directly related. Everything else held constant. Type of wire, diameter of wire, everything else constant. The length and the resistance are directly related. So if we have 0.4 ohms at 200 feet, now 500 feet, the 500 feet have to go on bottom because we have to line up feet with feet. We can cross, multiply, and divide. 0.4 times 500 divided by 20 is 1.0 ohms. Again, ohms have to line up with other ohms. Now that's not necessarily the only way we could set that up. We could have our ratio of links set up. We could just say 500 feet to 200 feet like that as well. And since the 0.4 ohms goes to the 200 feet, the 0.4 ohms is over here. That works as well. I mean, there are several ways you can set up these proportions. But notice, no matter how you set it up, you're going to be multiplying the 500 and the 0.4. And you're going to be dividing by the 200. So you get the same answer either way. So let's say we still have that 200 feet of wire. It is still 0.4 ohms. It has a diameter of let's call it 10 gauge wire, so 2.588 millimeters. You switch it to 200 feet, but we're going to go to 14 gauge. So this was 10 gauge. We're going to switch it out to 14 gauge wire. It has a diameter of 1.628. Millimeters. Will the resistance be more or less in this new wire? Same length. This other one had a bigger diameter. This one has a smaller diameter. We reduce the diameter. What we're really comparing is the cross-sectional area. But we reduce the diameter, we reduce the cross-sectional area, it increases the resistance. That is an inverse relationship. Generally, how we set that up, the way the packet sets it up, resistance 1 compared to resistance 2 is the inverse ratio. You flip the ratio of the areas. So we've got to find the area for these. Now we're given the diameters. We all know the area for a circle is pi times radius squared. You've seen that before, right? But since we're given the diameters, rather than dividing the diameters in two, we're going to use an alternative formula for the area of a circle. The area of the circle is pi times diameter squared divided by 4. Radius is half the diameter. Once you square it, it becomes 4. 2 becomes a 4. So the area here, I'm just going to use 3.14 for pi, times 2.588 squared divided by 4. So 5.258 millimeters squared. That's that area. Down here, for this diameter, 3.14 times 1.628 squared divided by 4. 2.5081, it looks like. So 2.081 millimeters squared. That is less than half the area. So it's going to end up being more than double the resistance. So now R1 was 0.4 ohms. Area 2 goes up here. That's going to be 2.081. It's area 2. This is area 1 because it goes with what we used for R1, 0.4. So area 1 goes on bottom then, the 5.258. And we'll cross multiply and divide. 0.4 times 5.258 divided by 2.081. So 1.01 ohms. Now, rather than calculating the area, let's look at this formula right here for a second. Area 1 is equal to pi times diameter 1 squared over 4. Area 2 is pi times diameter 2 squared over 4. So that ratio, area 2 over area 1, is pi times diameter 2 squared over 4 over pi times diameter 1 squared over 4. Looking at those, we can actually just cancel out the force and the pi's. So the ratio of area 2 to area 1 is just the ratio of diameter 2 squared over diameter 1 squared. So we don't have to go through figuring out that radius or that area every time from the diameters or from the radii. So for this one, we could have done R1 is 0.4 ohms. We're looking for R2. Diameter 2 goes here, which is the 1.628. That has to be squared. Diameter 1 goes down here, 2.588. That'll be squared. So that when we cross multiply and divide, we just enter it as 0.4 times 2.588 squared divided by 1.628 squared. So it's 1.01, exactly what we had before. Ohms. In the 12 packet that you guys have, on page 277 of that packet, is a table that gives the standard gauges and their diameters. Now, I've been using millimeters just because it's simpler for me. In English unit, a mil is a thousandth of an inch. So if it says 101.9 mils, that's really 0.1019 inches. That's just under a tenth of an inch, just so you know. What's that?
Well, I was just looking at the gauges. I don't understand
a 30 gauge is really, really thin. I've never really seen anything used below a 24 gauge, really. Okay, so the next step then is we're going to deal with well, let's just look at this. Let's say that 14 gauge wire is rated for 10 amps, right? If we are dealing with 40-meter piece of wire, what type of power is being used, dissipated in the wire, lost in the wire? For that, if it's running at full capacity at 10 amps. So, to figure that out, 14 gauge wire, we look in that chart, page 277, 14 gauge wire is 1.628 millimeters in diameter. If I want to know what its resistance is for a unit of length, I need to know its resistivity. Now we'll get into actually figuring out the resistivity from the diameter and the material in a little bit. For right now in that chart, it says 14 gauge wire. The third column there is 8.285. That is ohms per kilometer, right? A kilometer is how many meters? 1,000, yes. So 8.285 ohms per 1,000. How much is that per 40? So cross multiply and divide. So 8.285 times 40 divided by 1,000 is 0.3314 ohms. So that is the resistance in 40 meters of that wire. That's making a lot of assumptions. It's assuming that it's running at rated temperature. Most electronic components are rated at 25 degrees Celsius. Okay, so now from here, how do we find the power loss? Well, power is equal to current times voltage, but if we don't know the voltage, it's current squared times resistance, correct? So the power loss here is 10 amps squared times 0.3314. So our power is going to be 33.14 watts lost in the wire. We can actually use that to find a percentage loss. Assuming this is a 110 volt circuit, because 14 gauge wire wouldn't be used for 220. The power produced in the circuit is going to be simply that 10 amps times 110 volts. It's 1,100 watts produced. So the percentage loss here, percentage size over 100, our loss is 33.14 over the 1,100, which is the amount generated. Cross multiply and divide. .01%. has a 3% power loss. And just 40 meters of wire. 40 meters of wire is like 130 feet. So it's not a lot of wire. Does that make sense? Any questions? Okay. So you can use that chart, and it's all about, you know, ratios. Like I said, the ohms per kilometer, just turn that into ohms per 1,000 meters. Then it's really easy to figure out the resistance in a certain length of wire. So our next step, our second step, is we want to look at resistivity. If you flip in the packet to page 280, very top of that page is a table with the common resistivity of certain types of conductor. Now, you guys probably never use a silver conductor. Silver is the best conductivity of precious metals. They use gold a lot in things that are really, really sensitive. Gold actually has slightly better conductivity than copper, but it is not as good as silver. Can anybody think of why we would use gold instead of silver? It is soft, it's flexible. What's that?
I thought gold was like a softer, like less heat resistant.
Not necessarily heat resistant. Both gold and silver actually melt at relatively low points.
Okay.
The big advantage to gold over silver is silver tarnishes like crazy. Gold actually does not tarnish very much. Now you get gold jewelry and stuff, you really don't have to clean it that often because it doesn't take on a lot of tarnish. Silver, have you ever seen an antique silver place setting for silverware? That stuff will actually turn black in a matter of a few years if it's not cleaned. So that's the biggest disadvantage to silver. And that's why it's not used real commonly outside of systems where it's almost completely coated or submerged, where it can't tarnish. Silver isn't used. Copper is our main one. Copper does tarnish, but as long as it maintains contact, it won't tarnish internally like silver will. Silver tarnish will actually penetrate the surface. Aluminum was used a lot in the 70s and into the early 80s. They actually have aluminum wire in some houses out there. Anybody know why they switched from copper to aluminum? It was lighter. Cheaper was the big one. In fact, copper prices in the 70s were about where they were at a few years ago. Copper was up. You're getting like 30-some cents a pound for it. Or sorry, not 30-some, like $3 a pound for it, like $2.95 to $3.05 a pound for copper. I know at one point I cashed in like 142 pounds of copper and got like $420 for it. But and actually right now the copper that would be in a penny is worth way more than a penny. That's why your modern pennies since 1982, they're actually zinc with a very thin layer of copper on the outside. So there's very, very little copper in a penny anymore. The problem they had with aluminum. It's what they call work hardens. You're familiar with heat treating to harden a metal, like your tools and stuff are all heat treated to harden them. There's two ways to harden a metal. One is to heat it up to a certain temperature specific to that metal, and then quench it, cool it down really quick by either dipping it in water, blasting it with cold air, dipping it in oil. Another way is something called cold working. If you take a piece of metal and you bend it, anybody ever taken a wire and broke a wire by bending it back and forth several times? Yeah. What's happening is every time you bend that wire, that spot where the wire bends gets cold worked. And what it does is the atoms in there get rearranged. And when they rearrange, a metal is a crystalline lattice, and that lattice is perfect. And the more perfect that lattice is, the softer the metal is. Well, every time you bend it or smash it or stretch it, that lattice gets imperfections in it. Well, those imperfections actually make it stronger, but they also make it harder. So when you're bending that wire back and forth, you're creating imperfections, and the imperfections stack up until it gets so hard that when you bend it, it just snaps there. Aluminum cold works really well. It gets really hard relatively fast. So aluminum in a wall, it doesn't have to bend back and forth too many times before it gets really hard and brittle, and it'll eventually crack. So if it's in a spot where that wire is going to flex at all, you have issues. Installing aluminum wire, they had to be careful, because if you bend it back and forth too many times, copper wire, you can bend it this way, bend it back, work on then finally bend it and shove it in there and attach everything. Well, aluminum, you didn't want to do that. You didn't want to bend it back and forth too many times, because if you did, it would rather quickly, inside your insulated sheath, it'd rather quickly create microfractures in it. And when there's a little crack in the wire like that, now I'm going to exaggerate it for a second here. Well, now there's a mess with the conductivity. You have like a transmission loss or whatever, because even if they are staying tight together, you're still going from one contact to another. It's like having a splice in it. And yes, it has a higher resistance, and when there's a higher resistance, it creates what? Heat. Well, unfortunately, not only does aluminum cold work really fast, it also heat treats at not a whole lot above room temperature. It doesn't have to get very hot to heat treat and get even more brittle. So any sort of a spark jumping would heat it up, and it would get very brittle. In fact, as that gap widened at all, a spark jumping, a lot of people don't realize when a spark jumps, it actually has quite a bit of force to it. There's a little bit of a kick to it. So as the surfaces of this got hard and brittle, the spark jumping would actually cause chunks of the metal to chip off. And it actually just crunched this up, and it almost became like little stones inside that wire. It almost powderized the wire. So that now it's really jumping, and eventually that got to where that spark, the further a spark has to jump, the hotter it is. So it got to where finally that spark was jumping far enough to create enough heat that it caused a lot of fires. To the point where insurance companies no longer will not insure a home that has aluminum wiring in it. I made a lot of money in the 90s, early 2000s inspecting homes, because there were still a lot of them out there. Well, not a lot of them. There were still a number of them out there that had aluminum wiring in it. There were several that were found. I found one over here by Cumberland. They had actually taken the wires, and because you open the electrical box, pull the cover off the panel, and you look at the wires going into the breakers, and if they were gray, they were aluminum. If they were copper colored, they were copper. Well, one of the things they did is they'd take the wires, they'd go back a ways, cut them off, run copper into the box, and splice them to the aluminum, so they didn't have to rewire the whole house. I found one over by Cumberland that was done that way. It's dirty, but it's. So what you end up having to do is you end up having to go upstairs and take off covers for outlets and stuff and pull them out and look at the wires. And I've run into one that I can remember where they actually spliced wires onto the outlets and pushed the aluminum out the back, spliced them together and pushed the aluminum out through a hole in the back of the box. So there's copper in the boxes.
They probably didn't know what they were doing at that point. It seems like less work to just rewire the whole place.
Well, by the time you try to stretch wires through the walls, you're either going to have a really good fish tape, hopefully tie the wires together and pull them through, which usually doesn't work, or you're going to be punching holes in your walls. I mean, I've seen it where you cut holes like every foot. If you're running between studs, you cut a hole between every stud so you can drill through. I've seen them in a stud wall actually cut a groove. They've got a saw that's actually made to cut a groove, because it has to be at least an inch away from the surface of the stud. So they've actually got a saw that's got a 1.5 inch depth, so it cuts through a 1/2 inch of sheetrock and then an inch into the stud. And it's 1/2 inch, 5/8 of an inch wide. They actually cut that groove right through the wall so you can come and stick new wire in that groove and then fill it with sheetrock mud, patch it over. Not a fun process. So aluminum, moral of the story, aluminum no good. So anyway, one of the ways that we would test is we would go to an outlet where we could pretty accurately figure out how long the wire had to be to get to that outlet. And we would actually test to see what the resistance of that wire was. And from that resistance, then we could calculate what type of material that wire had to be. In a wire, the resistivity, that's the Greek letter rho, is equal to the resistance of the wire times the cross-sectional area, the area of the circle of the wire, over the length. Now remember, area is that's that pi times diameter squared over 4. In this form, it's not terribly useful. Generally, we would solve it for the resistance. This is actually the form I used it in when we were testing, by the way. You'd have the area of the wire, you have the gauge of the wire, the length of the wire, find the resistance, and this formula would give you the resistivity. For most of what we're going to do, we're going to be looking at the other way, solving for the resistance. So you'd multiply by L and then divide by A. So the resistance is equal to the resistivity times the length divided by the area. So if we have a copper wire, let's say we're going to have a number 12 copper wire. That is, let's say we're going to go with, so I keep it easy. We're going to go 100 meters long. So we're going to go back to page 177, or 277, and we're going to grab number 12, 2.053 diameter. Top of page 180, the resistivity is given in ohm meters. That's ohms times meter, which means the length has to be in meters and the area has to be in meters squared. So what that means is to find the area of this, the cross-sectional area of this wire, we would convert that into from millimeters to meters. So that would be you guys learn engineering notation last semester, scientific notation, engineering notation? A little bit? Okay. Milli is 10 to the negative 3 meters. A millimeter is 10 to the negative 3 meters. If I square that, that would be 10 to the negative 6, right? Look very carefully at that chart on the top of page 280. The resistivity is given as for copper 0.0172 times 10 to the negative 6. So the way it works out, if I use millimeters for my diameter, instead of converting it to meters, the 10 to the negative 6 cancels out. Does that make sense? So what I'm going to use then here for my resistivity, instead of 0.1 or 0.0172 times 10 to the negative 6, I'm just going to use 0.0172. I'm going to multiply that times my length of 100 meters. I'm going to divide that by my area, which is going to be pi times 2.053 squared over 4. So I'm going to punch that in my calculator. See what I come up with. 0.0172 times my length of 100 meters divided by, now I'm going to put this in parentheses here, pi is going to be 3.14 times 2.053 squared divided by 4, close my parentheses. Hit enter, I get 0.5199 ohms. So that 100 meter piece of wire, number 12 wire, should be 0.5199. Let's compare that, just for fun. Back to page 277. Number 12 wire is 0.5211 per kilometer. So it's 0.5211 ohms per 1,000 meters. How much is that per 100 meters? Cross, multiply, and divide. Oops, that should be 5.2, not 0.52. So 5.2, we cross, multiply, and divide. This should be 0.5211 ohms. So that calculation comes out really close. 0.521 and 0.519 are pretty darn close to each other. Obviously, it's round off errors that make it not quite perfect. So, if we have a wire that is estimated to have a length of, oh, let's see, let me put this length in. Let's say we're going to estimate it has a length of 80 meters. It's number 14 wire. Copper. Well, let's say we're not sure if it's copper. We're trying to decide if it's copper. What would we expect this to be if it were copper? Well, the resistance is going to be resistivity of copper, 0.0172 times that length of 80 meters over pi times. Number 14 is what? 0.1. Sorry, 14 is 1.628 squared, and then of course over 4. So, spot that in there. 0.0172 times 80 divided by, in parentheses, 3.14 times 1.628 squared divided by 4, close the parentheses. I would expect that to have a resistance of 0.6614 ohms, approximately. What would I expect it to be if it was aluminum? Well, if it was aluminum, instead of the 0.0172, it'd be 0.0283 times the 80 meters over pi times 1.628 over 4. Assuming it's still a 14 gauge wire. Which is going to give us a resistance of 1.088. Wait, 0.882 ohms. So you see it's not quite double, but it is close. So when testing that wire, if you have a reasonably accurate estimate of that length, it is not difficult to tell if that resistance is correct or not. The biggest thing that would interfere is if it goes to a hidden junction somewhere and you can't see that it's a junction, that connection loss is, the insertion loss, I guess is kind of the term they use for it. When it goes through a connection, that'll screw you up. Last thing for the day is I want to talk about thermal issues. If, let's say that a piece of wire has a resistance of 0.34 ohms at 28 degrees Celsius. Find the resistance at negative, I'll go negative 12 degrees Celsius. When it gets colder, do you think resistance goes up or down? It would make sense that it would go up. Actually, most materials, it goes down slightly. The relationship that copper, if we're dealing with copper, I should say, the relationship with copper is copper has zero resistance at negative 234.5 degrees. Every metal, every conductor has a temperature that if you can cool it down to that temperature, it becomes what we call a superconductor. It has zero resistance. For copper, that is negative 234.5 degrees Celsius. Every degree above that, the resistance increases. So in order to gauge the resistance, we actually have to go by how many degrees it is above negative 234.5. So the relationship here, R1 to R2, is equal to temperature 1 plus 234.5 compared to temperature 2 plus 234.5. So in this case, we have a resistance of 0.34 ohms at 28 degrees. So that's 28 plus 234.5. We want to know what the resistance is going to be at negative 12 degrees. So it's negative 12 plus 234.5. So I'm just going to add here. 28 plus 234.5 is 262.5. Negative 12 plus 234, well, that's 222.5. So I'm looking for this resistance right here, R2. So if we cross multiply and divide here, 0.34 times 222.5 divided by 262.5 gives us 0.288 ohms. So that's significant. That is nearly a 20% loss in resistance for going 40 degrees cooler. Okay, with that, in this packet, page 275 and page 279 deal with the wire length and wire diameter. Remember, page 277 is where that chart is as the wire gauges and their diameters. Page 281 and page 283 deal with the resistivity. It's 1 through 6 on 281. 283 is just 1 through 4. We'll have you work on those. Our next topic to deal with, our last topic for Unit 1, we're going to talk a little bit about binary numbers. So what I want to do is I'm going to pass out a packet for you guys on binary numbers. Yep. So you already got one, right, Andrew?
Yep. Where did mine go?
I'll give you this packet on binary numbers to work on.
Right. You want us to start on it?
Read through it. We will talk about it more. What I'm thinking is for tomorrow, Woods completely shut down classes yesterday for career day, so there were none of them in here. So I'll probably spend a lot of the time tomorrow with them. So if you do these 4 pages out of the 12 packet, and then just read through the binary numbers packet. See what you can figure out.
I thought it was 2 pages.
Well, there's four. There's four. 275, 279, 281, 283. If you work on those 4 pages and just read through the binary numbers packet, we'll count tomorrow as a work day for you.
It's not mandatory to show up.
So it will be mandatory to show up. But on Monday, we are going to blast through binary numbers pretty quickly. Yep, there are problems in there to do.
You want to start on them?